Okay, good morning everyone, and welcome to today's GSC43 technical session or webinar, where we'll be discussing the CC-Link I-Field Basic to MRJ5 control. Before I go any further, can I please just get an indication that you are able to see my screen?
Now we can only see the entry screen.
Yeah, that's fine then. Okay,
There we
yeah.
go.
Okay, no problem. Okay, so the GSC43 can interface with a Mitsubishi Electric servo drive using CC-Link I-Field Basic, as CC-Link I-Field Basic is one of the supported communication protocols of the GSC43. The MRJ5 servo motors, as well as the MRJ-ET servo motors or servo amplifiers, actually also support CC-Link I-Field Basic. So the GSC43 can be used with either of these two servo amplifiers. So the objective for today's demonstration or webinar is to demonstrate the control of a MRJ5G servo via CC-Link I-Field Basic using the GSC43 as the controller. So the hardware that I have next to me today is the GSC43, which will be our HMI and controller, the MRJ510G RJ servo amplifier, and then the HK-KT053W servo motor. The software that I'll be using today will be CODESYS and MR Configurator2, with CODESYS being used to program the GSC43 and MR Configurator2 used to parameterize our servo amplifier. So just to give you an overview of the functionalities that we'll be adding to our demonstration or to the demonstration today, we'll be adding the servo on command, jog forward and reverse commands of operation, home return command, positioning command via a positioning table. We're gonna be able to reset and clear alarms, and then monitoring things such as the position, operation mode, and alarms. So just to start off with some overview on CC-Link I-Field Basic. So CC-Link I-Field Basic is an industrial automation communication protocol that is based on standard Ethernet. It uses cyclic communication to transfer data between your master and your remote station using link devices. So link devices, it's basically just registers that are used to transfer or store the bits or registers that need to be transferred between the master and remote station. On the right, you can see the diagram for the flow of data transfer of the link devices, and this will include your RX, RY, RWR, and RWW link devices. Your RX and RWR link devices are used to transfer bits and registers respectively from your remote station to your master station. So essentially it's reading from the remote station to the master station. Whereas the RY and RWW link devices are used to transfer bits and registers from your master station to your remote station. Now, each station gets assigned a certain amount of link devices, or a set amount of link devices. And this amount equals 64 bits for your RX and RY, and 32 words for your RWR and RWW. So each station added to your configuration. So if you have multiple remote stations, each of those stations will be assigned this amount of bits. The user cannot edit this, and the mapping associated with these bits is also defined by the manufacturer of the remote station. So each, and there usually is also a limitation on the number of remote stations for CC-Link iField Basic that can be connected to a master, and this will depend on the master device. So having said that, as we said, the GOC supports CC-Link iField Basic as a master configuration. It does not support a slave configuration, but that is fine as we are wanting to use the master configuration today. So as I said, each master station might have a limitation on the amount of CC-Link iField Basic remote stations that can be added to it. And for the GOC, this is 4 stations. So you have 4 allowable stations that form part of your maximum 8 Ethernet connections that you are allowed to connect to the built-in Ethernet port of the GOC 43. That still leaves 4. So if you do connect 4 CC-Link iField Basic stations, that still leaves 4 connections for Modbus TCP or an FTP server configuration. The addressing of the link devices in the GOC memory is defined by the user, so it doesn't get assigned automatically, and it is also not assigned in the communication protocol interface memory area, but rather you define it within the marker memory area, which is the %M memory area of the GOC. So when looking at how to configure the GOC as a CC-Link iField Basic master, this is done via a function block. So the function block is provided by Mitsubishi Electric within the GOC toolkit library, and it is the GOC 43 underscore CCB documentation or library as well. So in your install for CODESYS, you'll see the GOC Toolkit v3 folder in which you'll find manuals and library manuals. So there you can also see the documentation on how to use this function block to configure the CC-Link iField master station. So starting off, let's actually go over to CODESYS. Just give me a second. Okay. So starting off with importing the function block, you open the library manager in your device tree, right click within the window, anywhere is fine, select add library, then this pop-up window comes up, go to advanced, miscellaneous, and then you'll see the GOC 43 underscore CCB library. This is what the function block for the master CC-Link iField Basic master configuration. Clicking OK will now import this to my program. So once you have imported this to your program, you are able to use it within your program. So I actually have set up the configuration beforehand, as I will be going through the presentation breakdown as it's a bit easier. But yeah, so if you do import your function block, you do it by dragging and dropping a box, clicking on the box itself, going to the action button, which brings up your input assistant, in which you can select the function blocks tab, and then you should be able to see the library that you have imported. So if I click OK there, I have now imported the function block once again. Note, you only require one of these function blocks for your GOC43, as one of these function blocks can support up to 4 remote stations. So just quickly going back to the presentation. So this is just the steps for the library and adding the function block that I just showed you. Now, looking at how to configure the function block, we start off with our inputs and start off with the first input being run. So this just enables the function block to set up the communication. Whenever this input is false, communication is stopped to all remote stations. Next is the number of stations. So this is where you set up the number of slave devices or remote stations that you are connecting to the GOC. As mentioned, the range is 1 to 4. Do not exceed 4, as this will cause errors. Next is the CC-Link iField basic station list. This also configures your stations, but this configures the IP address, or, well, more like the station number of each of your remote stations. So the way to declare this is via the array or an pointed to an array, the declaration which you can see at the bottom here. So one thing to note about this input, the station number is equal to your remote station's fourth octet of its IP address. So if I look at, let's say, an example of 192.168.3.9 being the remote station's IP address, this will mean that I need to set 9 as its station number in this declaration. So that needs to be input into this input of the function block. Next is the timeout period input. This just sets the time period after which the master station should retry the connection to the slave station. And the counts input determines how many retries the master should attempt. This can be set as 3, 5, or 10, none other than these options. So the next input is the reset diagnostics or reset. So this determines what action is taken, what reset action is taken. So when setting 0 here, no reset action is taken. When setting 1, reset output parameters, your minimum and maximum link scan time. 2, clears the error code if the cause of the error has been corrected. 3, resets the action as per 1 and 2, so it combines the second and third reset actions, and if you set it anything higher than 3, there will be no reset action. Next is where you declare the starting addresses for your link devices. So if you recall, I mentioned that the link devices are declared by the user, and this is where you do it. So this declares the starting address of your RX, RY, RWR, and RWW. Now keep in mind that each of these have a set amount of link devices assigned per station. So if I have multiple stations, I need to leave enough space for my memory or for my addresses that all of these stations addresses fit in the ranges that I set here. So for instance, if I set my RX starting address as a percentage MB3000, I need to keep space for, if let's say I have the maximum 4 amount of connections, I need to keep space for 64 times 4 bits, which is pretty easy. But yeah, so that needs to be kept in mind for all 4 of these addresses. But for today, we only have one remote station, so that is not really a problem, although the addressing here is also declared pretty spaciously. So note that this is only the starting address, and therefore the addressing will happen or be assigned according to this starting address. So this will mean that RX00 will be in 3000.0, as this is a bit, but the moment it goes to words, it will not just occupy a bit. Okay. Next is the slave info. So this is a pointer to a structure or array that stores diagnostics of the slave station, and some information as well. So this includes vendor code, model code, device version, slave local unit info. Yeah, quite a few things. It can store the error code. It can store comms error. So you can use this information to determine which of your slaves are in error and determine whether you need to do any check any communication cables or the configuration itself. Now, going to the outputs of this function block, the first is the done output. So this is a Boolean type output. And this is where you can see whether the configuration has been successful. So when this is true, the configuration has been successful, and when this is false, the configuration has an error has occurred for the configuration. Now, when an error has occurred, you're able to see it in the error underscore com, or well, yeah, you'll see the error code. So the error code will indicate what type of error has occurred. If error underscore com is 0, then no error has occurred. When it's one or more connected slave stations are not communicating. And if it's 2, multiple master stations exist on the same network. Now going to the error config. This also give you a bit more indication on what error could have possibly occurred for the done output to be false. So the first option for this is 0, no error. 1, station number is invalid. So that means you've selected a station number out of range. 2, address overlaps or out of memory area assigned marker memory. If the error code is 3, the number of slave stations or number of occupied stations is out of range. 4, same station number configured for more than one slave. So that means most likely you also have a duplicate IP address for 2 of your slaves or remote stations. When it's 5, your master station IP address matches with one of the slave stations. 6 to 7 is reserved. 8 means that the count value is anything else other than 3, 5, or 10. And 10 means that the master function block is already configured. So that means you have configured more than one master block for your GOC. Next is the maximum link scan time and minimum link scan time. This just indicates the minimum and maximum cyclic transmission or cyclic communication time, scan time, as well as your current link scan time is just your current cyclic communication time. So when declared, this is approximately how your variables declaration for the function block should look. And this has all been done within the last few slides. And this is approximately how your function block should look when configured. Okay. So now that we've discussed the configuration for the GOC for CC-Link I-Field Basic, let's look at the MRJ5. So as stated, we are using the MRJ5 10GRJ servo amplifier for this demonstration. And this servo amplifier forms part of the MRJ servo range, which is one of the newest ranges. The G-type servo amplifier of this MRJ5 range is the servo amplifier that supports CC-Link IE TSN as well as CC-Link IE field basic communication for the servo motor control. So the G-type MRJ5 servo motor amplifier comes in a 1, 2, 3 or 3 axis configuration, but just a special note for the CC-Link I field basic, there's only a single axis available. And if we look in more to the exact model that is being used for today's demonstration, the servo is a single, or servo amplifier is a single axis servo amplifier that has a rated output kilowatts of 0.1. You can see the model designation on the right hand side. The servo amplifier will be used with the network protocol set as CC-Link I-Field Basic for this demonstration, as this is what the GOC supports. But something to note when using the MRJ 5G type amplifier is that there are some limitations when using the CC-Link I-Field Basic protocol. So these restrictions include some features that are not available, such as a 2-axis servo amplifier, a 3-axis servo amplifier, some of these cyclic synchronous operation modes. Yeah, there's quite a few things. And then there are also some that are available for the G-type amplifier, but they are only available from a certain firmware point onwards, and that you'll have to look at the manual for that information. Yeah, so one thing to take note of is the control modes that aren't available for CC-Link I-Field Basic, which is these that you see here, as you won't be able to use those. You won't be able to use those in your operation. So when it comes to control modes that the MRJ 5G does support for CC-Link I-Field Basic, this includes the profile position mode, the profile velocity mode, profile torque mode, homing mode, point table mode, and jog operation mode that you can see here. Now, the servo amplifier uses parameters much like a VSD to configure its operation, and this is done via MR Configurator2. So before we go on, just gonna quickly open MR Configurator. Okay. So when it comes to the network parameterization for the MRJ 5G, we will have to look at setting the IP address, subnet mask, network protocol setting, and in some cases, the communication speed. So this is because this determines the characteristics of communication between your controller and your servo amplifier, in which case we want to set CC-Link I-Field Basic. We need to set an IP address as well as a subnet mask. So for the IP address, there's actually two methods of setting your IP address. The first being the rotary switches on the front display of your servo amplifier, which you can see an image right here. So switch 1 and switch 2 can be used to set your fourth octet of your IP address, also your servo amplifier IP address, with octet 123 being taken from the parameter in the of the servo amplifier, which by default is usually 192.168.3.1. So one thing to note, if both your rotary switches are set to 0, the default IP address within the parameter will be used. So the parameter that sets your IP address is NPA02, and then NPA01 is used to set whether you want to use your rotary switches or the IP address set within your parameters. So if I quickly go over to my MR configurator and go to my network parameters, you'll be able to see I can set use parameter or use rotary switches in NPA01. And then that is NPA202 is where I can set my IP address. So when it comes to setting your subnet mask, there's only one way of setting this, and this is via the NPA04 parameter, which is actually just underneath the IP address parameter, as you can see here. So next setting or next parameter that needs to be set is the network protocol setting. So this is where we set whether to use CC-Link IE Field Basic or CC-Link IE TSN. Now this is set in parameter PN, apologies, it's set in parameter PN13 bit 023, and to do this you need to set 004, or if you just go to your parameter list common, you should have this option under network protocol setting where you are able to choose between the two. So the protocol set for this will be CC-Link IE Field Basic. So the communication speed setting parameter is actually not necessarily applicable for this demonstration, but it's important to keep in mind when using CC-Link IE TSN, as this determines whether you're using 100 megabytes per second or 1 gig per second communication speed when using TSN. But for the CC-Link IE Field Basic, regardless of what this value is of this parameter, it will stay as 100 megabytes per second. And just a note, whenever any of these parameters have been changed, the parameters need to be written. So first go online via a Ethernet or USB connection to the servo amplifier and click on the switch online offline, and then select access writing, which will then write the parameters to your access. Once the writing has been completed, cycle the power of the servo amplifier for the parameter changes to take place. And that needs to be done for each of these files you see here. So if I change something in parameters, I need to write the parameter to the access. If I do change anything in my network parameter, that needs to be written separately. They aren't all written together. Okay. So next, we're going to look at the MRJ5 PDO mapping. So when I say MRJ or the PDO mapping, this is how these link devices for CC-Link iField Basic is mapped for the MRJ5. So this looks at the mapping of RY, RX, RWW, and RWR. So for your RX and RY link device mapping, this stays constant no matter what control mode you choose or operation mode. But when it comes to the RWW and RWR mapping, that changes depending on your control mode or operation mode that you choose. And we'll be going through the different types in a second. But first, looking at RY and RX, RY is mainly used to start the cyclic communication. So you'll see RY, and in this case 3F for a single station, will turn on your cyclic, or is your cyclic communication ready command. Whereas your RX 3F will be the cyclic communication ready status. So that's what you'll be reading from the remote station or the servo amplifier in this case. Now, to go on to the RWR and RWW link devices, as I said, these do change depending on what is set in your control mode selection parameter and your default mapping mode selection. So these are two parameters in your servo amplifier that determine what control mode you are able to use and what mapping mode selection. So to give a bit more clarity, your control modes that are available for CC-Link iField Basic is the network standard mode and the positioning mode or point table method. And next, the default mapping mode selection determines whether you are using 2 touch probes, 1 touch probe, or 1 touch probe and an input device. So that ultimately determines how your link devices are mapped. So when it comes to your control mode selections, how your control modes are grouped within these two categories, you have once again your network standard mode, which allows you to do profile position mode, profile velocity mode, homing mode, and last but not least, profile torque mode. Now, the other category is the positioning mode. This allows you to do jog mode, homing mode, and point table mode. So only one of these two groups can be set on the amplifier at any given time. So whatever you choose, you are limited to the control modes that group has access to. So how this actually works is you can change between these two groups during operation via an SLMP signal. However, this is something that the GOC does not support, but if you are, let's say, using the FX5, you will be able to switch between these two modes. But for the GOC application, this is not possible. So you will need to choose one of these two modes for the operation that you want to perform. And then, yeah, as I said, the default mapping mode is just to determine what peripherals or input devices or probes you have connected to your servo amplifier. So for the purpose of this demonstration, we'll be choosing the positioning mode. So therefore we'll be using the point table, and we'll be choosing the default mapping as 0. Therefore, 2 touch probes will be registered to the mapping, although this will not affect anything because I do not have any touch probes connected or installed on my servo amplifier. So this is set via parameters. Apologies. So this is set via parameter pn22.0 being equal to 0. So now looking at what this means for our mapping, and just note that this is specifically for positioning mode for mode 0. And I'll show you in the manual as well that there is various tables just like this one. So when it comes to the RWW PDO mapping, we have register 0 being the modes of operation, register 1 being the control word, and then we have some control digital inputs. Register 6 is your target position, which is something that will be used quite a bit. Register 8 is the target velocity. Then you also have your velocity limit value, you target torque, profile velocity, profile acceleration, profile deceleration, torque slope, and so on and so forth. So this is important to know because this is the actual registers that you'll be using within your PLC program. When it comes to the RWR PDO mapping, you also have a modes of operation display, so you can monitor what mode of operation the servo amplifier is currently in, and then you have your status word. And just looking at what we'll be using today, the position actual value, so you can track what position your servo motor is in, your following error actual value, your current alarm, and so on and so forth. Now, for your control word and your status word, those can be further broken down. So, looking at your control word, you have bit 0 being switch on, bit 1 being enable voltage, bit 2 being quick stop, bit 3 enable operation, and then we start looking at bit 4, 5, 6 that have OMS. So all that when you see OMS, this is operation mode specific. This means that the function of this bit depends on what operation mode the servo amplifier is currently in. So as you can see on the right hand side, there's a breakdown of what this bit does when set to or different operation modes. So for instance, when it is in profile position mode, bit 4 of the control word will set a new set point. In the case of homing, this will set the current position as the home position. For jog, this will start the motor movement or motor operation. And for the point table mode, which is this one minus 101 here, this will also set a new set point, so it will start a new sequence. When looking at bit 5, it is also a operation mode specific bit, and looking at the table on the right hand side for profile position, this sets whether to execute a set of set points or just a single set point, and for the jog mode, it determines whether your motor is jogging in the forward or reverse direction. So each of the OMS bits have a function to them. As you see here, operation mode 6 or specific bit 6 determines whether your profile position is done in absolute or relative position commands. So bit 7 is actually your fault reset command. So this resets the servo amplifier when it is in in an alarm state or an error state. Next is your halt bit, but this is also, so your halt bit is also an operation mode specific, but as the halt operation depends on what mode you are currently in. So halt is basically how the motor is stopped. Last but not least, bit 9, which is your also an operation mode specific bit, determines change on set point for the profile position mode. Although this will not necessarily be important today, so because we'll be using jog, point table, and home mostly. Now the status word equal to the control word can also be broken down, with bit 0 being the ready to switch on bit 1 being the switch on bit 2 being the operation enable bit 3 being the fault bit 4 the voltage enabled bit 5 the quick stop bit 6 the switch on disabled bit 7 the warning, 8 is a reserved bit, 9 is the remote bit, so it determines whether the control word is being followed or not, or it indicates whether it's being followed or not. But 10, which is also an operation mode specific bit, which I will be expanding on in a moment. 11 is your internal limit active bit. 12 is also 12 and 13 are also operation mode specific. So when looking at your operation mode specific bit for 10, it in general indicates whether the servo motor has reached its target, but its status does differ depending on what control mode is being used. As you can see, there's quite a bit of information here regarding this. So when looking at the homing, you can see that there it shows that different states of bit 13, 12, and 10 indicate whether 1. Homing is in progress, homing procedure has not started or is interrupted, homing has been attained but target has not been reached, homing procedure is completed successfully, or homing error has occurred in some manner. When it comes to jog, this bit also indicates where the target has been reached. The same for the point table. Okay. Yeah, same for operation mode specific bit 12 for your status word. When looking at, let's see, the point table method, this indicates whether the set point has been acknowledged, and this is not applicable for jog, but it is applicable for homing, which depends on the information you see in operation mode specific bit 10. Okay, so that is the configuration for both your GOC and the servo amplifier for CC-Link I-Field Basic. Now, starting to look at the demonstration, we'll look at some of the servo parameters that don't necessarily affect the CC-Link I-Field Basic communication protocol, but that are necessary for your servo to function or operate as you intend it to. Now, obviously, this is very much dependent on the application that the motor is going to be used in. So the parameters that I set here will not necessarily be used for all applications. These parameters will depend on the specific application. So first parameter that will be looked at or be set is the forced stop parameter. So I do not have a forced stop wired into my servo amplifier, meaning that I need to disable this functionality, and this is done by setting the disable in parameter PA04.2 and PA04.3. So if I go to my MR configurator, you'll see that the force stop selection is disabled in both 4.3 and 4.2. If this is not done and there is no force stop wired into the servo amplifier will remain in an error state. Next is the operation mode selection. So you have three types of servo motors: a standard rotary servo motor, a linear servo motor, and a direct drive servo motor. For this demonstration, you have a standard rotary motor, and in this parameter, is where you set what type of motor you use. So in parameter PA01.1, we keep it on the default, which is standard control. So if you just quickly go back, if I expand, you can see you are able to choose between linear, direct drive, or standard control mode. One of the more important parameters to set is the electronic gear parameters. So this will be your electronic gear numerator as well as the denominator, which is parameter PA06 and PA07. Now, your electronic gear ratio determines the travel distance per servo motor revolution. So this is important to set how you would like it to function. Now, the equation used to determine your electronic gear ratio can be seen. It's the encoder resolution over the travel distance per servo motor revolution. So one thing else to note on this, the unit in which your travel distance is measured will depend on what is set in parameter PT01.2, as this determines the unit for position data. So for this demonstration, we are currently using pulses. But you are able to set this in millimeters, inches, or degrees. So your gear ratio will also depend on what you have set there. So the encoder resolution for the motor that's been used for this demonstration is 67,108,864 pulses per revolution. And the travel distance for a full motor rotation that is chosen is 300,000 pulses. This means that for every 300,000 pulses that I give my servo motor, it will rotate, its axis will rotate once, thus meaning that my electronic gear ratio will be as follows, as you can see on this screen. And this is set in PA06 and PA07, which if I just show you in the yeah, right here. So that is the electronic gear ratio. Now, there is a parameter that relates to how the homing method works, and this is parameter PT45. For this demonstration, it's set to -3 data set type, which means that the homing is done without a dog, as I don't have any dog proximity sensor connected to the servo amplifier. And this also means that when the home position command is executed, the current position is set as the home position. Also, just to show, this is set right here. So there actually are quite a few options for this, and it will also depend on what peripherals you have on your servo amplifier. Now, if you are ever working on MR Configurator and you're not sure what the parameters, different settings mean, you also have a docking help at the bottom. So whatever parameter I do click on, I can go read up more on the different options for settings for this parameter. So last but not least is the in position output signal on condition selection. This determines under what condition the in position signal turns on, which for this case will be set to 1, meaning that within the in position range and at completion of output command. So this means my in position signal will turn on when it's within a certain range of my position, as well as the completion of the output command itself. Now, as I mentioned, the control mode or method that we'll be doing or using for today's demonstration will be the point table. So this means that the point table needs to be configured as well. So to access your point table, go to the project tree in the project window and double click on point table. This will open this interface you see right here. So a point table is configured and stored within your servo amplifier, and this point table defines a series of target positions with speed and motion conditions that determines the servo motor operation. Each entry point or each row in the point table is one motion step. So I did show you where to access the point table in MR Configurator, which you can also see here. Now, looking at what each of the tables mean and what you configure in each of the columns of your point table. The first is your target position. So this is the position that you want the servo motor to move to, so the axis to turn. So this, once again, will be in terms of pulses, as that this is what has been set in my parameters. So if I look at the first entry here, I am instructing the servo motor to rotate 100,000 pulses in the positive direction or forward direction, which for this setup should be counterclockwise. I do mention this a bit later on, so we will get to that as well. The second column sets the speed of the operation. So if I once again look at entry 1, moving this 100,000 pulses, the servo motor will move at the speed of 100 RPMs. Next is the acceleration time constant. This determines how long it will take the motor to reach the speed that is set in the speed column. The decel time constant, so your deceleration time constant, just does the opposite of your acceleration. It determines, or it sets the time the motor takes to stop from this time speed set to complete stop, so 0. Your dwell time is the best way to explain it. Your dwell time is the time the servo motor operation pauses between each step. So as you currently see here, it's 1,000. Apologies, 1,000 is set, meaning after my servo motor has moved 100,000 pulses, it will stop at that position for 1 second before moving on to the next. Last, or not last but not least, second last is the auxiliary function. So the auxiliary function determines the motion operation, whether it continues or stops at this entry. So if I look at my setup, when using the point table in relative position command method, which is what we are currently doing, when setting 2 as your auxiliary function, operation is performed in accordance with a single point table selected. This means that if I do set 2 in the auxiliary function, only one position or point will be executed at a time, so it will not automatically go on to the next point. With 3 set, this does mean that it automatically moves to the next point without me having to input anything else. The same for 10 and 11, although there are slight changes between them. The last column that you can edit is the encode. This is just basically where you set an encode for the table or row entry. Now, setting up the point table for the functionality for today, we'll be looking at setting a home position and executing 2 different sequences. So starting with our home position, as it's currently configured here, this will be row or step 11. So this row commands the server access to go to position 0, so the home position in this case, at the speed of 100 RPMs with an acceleration and deceleration time of 100 milliseconds, so 1 second, and a dwell time of 1 second as well. And as you can see, the auxiliary function is set to 0, meaning that whenever 0 is set as well, this means that only the single step is executed. So this means that only step 11 will be executed when instructed to execute step 11. Next, looking at the sequences. So sequence 1 is configured from step 1 all the way to step 10. As you can see, the first instruction is to move 100,000 pulses in the positive direction, where the next one is to move 200,000 pulses in the negative direction. And then it keeps, the motor operation keeps oscillating between these 2 positions. With step 10, I'm ordering it to go back to the home position. Each of these steps are set up with a speed of 100 RPMs, acceleration time being 1 second, deceleration time also being 1 second, and the dwell time between each of these steps being 1 second. This means that after every step, the servo motor axis will pause for 1 second. The auxiliary function is set as 3 for steps 1 to 9, meaning that after the step has been executed, it will automatically move on to the next until it gets to 10, at which point the auxiliary function is 0, so it will stop at that step and wait for a new instruction. The second sequence is configured from row 12 all the way to 20. And this operation basically turns the servo motor axis 1 full rotation and turns it back to home, after which it pauses for 2 seconds. If you can see, this is my dwell time column, and that is set to 2000, which equates to 2 seconds. So after the full rotation and back to home position, it then moves to a 3/4 rotation, back to home position, pauses for 2, half rotation, back to home position, 2-second pause, and then a 1/4 rotation, back to home position, and another, or that is actually where the operation stops. So one thing you'll note is moving it, giving the instruction to execute 300,000 pulses gives it 1 rotation as set in our electronic gear, but then the next is instructing it to move another 300,000 in the negative direction. So for these settings, it doesn't necessarily refer to a position. It refers to the amount of pulses to be moved. But whenever you set the lost position, so when it doesn't automatically move to the next position, as you see for the last position, then it moves to the exact position and not just moves, it doesn't just move by the amount of pulses that you've set in the target position. I hope that makes sense. Okay, so that is the point table configuration. Yes, Dominic.
Sorry, I've just got a question.
Yeah?
If you enter unrealistic position data into that table, will
Yes.
it actually cause an error on the on the what's the name? The servo
Servo amplifier. So
buyer, yeah?
actually, it won't allow you to write the point table to the servo
Well,
amplifier.
it's got the
So
on top, it's got like the maximum minimum value.
yes,
So
yes.
if I
Yeah, it
were to
won't allow
put
you to.
in a correct value here, like the
Yes.
biggest one here, but the motor can't handle that, it'll give an error.
So that depends on if you have limit switches. So yes, if you do activate a limit switch because you input a unrealistic or unobtainable position, yes, it will cause an error. But that is also dependent on how you set up your system.
And the second question is, can I move within this table? Can I move, say, for example, in some condition, I'd like to move, let's say if it goes to step number 4, can I bring it back to step number 1? In other
Um,
words, will it execute only in this sequence, or can I play with the sequence from the outside?
yeah, so when we go to the programming, you actually tell it at which point to start. So if you do set it up to jump around within your PLC program, it is possible.
All right, thank you.
Okay, no problem. Yeah. So now we'll start looking at the PLC program, at which point I will be switching over to CODESYS and doing the programming alongside. Okay, so I have already created a CODESYS project for the GSC and did the CC-Link I-Field basic configuration. I've also set my PLC settings to the recommended settings in the manual, which is set all outputs to default, enable 2, and main task for your bus cycle task, setting up the connection to the GSC itself, the communications tab, and then scan for the GSC. Okay, just give it a second there. So that sets up the communication to my GSC itself. Okay, so looking at, I also created POUs to use for this demonstration, which is called within the main task. So that means that it actually executes in the scan time of the GSC. So the CC-Link I-field basic control will be done within this POU, where I also declared some variables. Now, just to point out, let's zoom in a bit. As you can see, I have declared variables for the link devices so that I, just for ease of use. So this, these addresses are determined by what has been set or configured for my master station or master configuration function block. So for RX, the start address is memory area byte 3000. RY, it's marker memory area byte 4000. For RWR, it's marker memory area byte 5000. For RWW, it's marker memory area byte 6000. So I've gone and declared the variables per that declaration, so starting point, and per the mapping. So if I can quickly just show you the manual. This is the mapping that I showed you previously in the tables. So if I quickly take a look at my positioning mode and mode 1, I can see that the first register for my RWW is the modes of operation, which I've set there. And this is set as marker memory area byte 6000. Now, one thing to note, CODESYS works in octal or bytes. So one word will take up MB 6000 as well as MB 6001. So I need to skip, or the addressing needs to skip or increment by 2 for every one of these registers. Now I've gone and declared the mapping in the applicable addressing and also set out the control word here as well as the status word here. And this is the variables that will be used. I've also set some control input and output variables for the HMI functionality. So the first step to programming or setting up the control of the MRJ5 is to start the cyclic communication. This is done by turning on RY 3F of the link devices. So to do this, I'll be setting up or initiating the cyclic communication on the startup of my GSC. So to do this, I drag and drop my contact, go into my input assistant, and then navigate to my system variables, in which I have the functionality of a always on bit. So this is in the sysvar CPU system variable in the system bits. So selecting that and then indicating that I want to use bit 0, as this is the always on bit of this system variable. So next, setting the cyclic communication command to be on when the GSC is running. So this is RWW01 control word. Sorry, it's RY3F, the ready command or the cyclic communication ready command. So that sets up the cyclic communication. So this is my start cyclic communication. And basically what this is doing, it starts the cyclic communication as long as the jersey is running. Okay. Now that the cyclic communication has started, we are able to give commands, so control commands to the servo and servo amplifier. So the next step is to turn on or give the servo on or enable operation command. So in many situations you'll use the servo on terminology, although in the CT-Link I field basic this is seen as the enable operation command. And to execute this command, you actually need to turn on a few different bits of the control word. So to just show you this, I'll be going back to the presentation. So the combination of different bits in the control word that are on equate to different statuses. So when looking at the enable operation, this requires bit 0, 1, 2, and 3 to be on for the servo motor to be in the servo on status or the enable operation status. So this means I need to turn on bit 0, 1, 2, and 4 for my servo to be on. Now to do this, I'll be using my feedback from the servo that indicates that the cyclic communication is ready. And I'll also be using an HMI button in which I'll be turning on the servo. So this is set up as HMI input bit servo on. There, this command. So as you can see, the variables declared for the HMI and the internal PLC logic are symbolic declarations as they do not have any addressing, and this falls in the data memory of the jersey. Actually, I'll just copy and paste. Okay, so turning on the bits that need to be turned on, as I said, it's control word bit 0, so it's RWW01 bit 0, which is the switch on bit. Next, it's also the bit 1, which is the enable voltage bit. Bit 2, which is your quick stop bit. Bit 3, which is the enable operation bit. So all of these bits need to be on for your servo to enter the enable operation or operation mode enabled status. So yeah. Now, as we want to display whether the servo amplifier or the servo motor is indeed in the servo on or enable operation status, we'll look at the bits that need to be on for the servo to be in this status. So let me quickly just go back to the presentation. So for the status of the servo amplifier to be in enable or operation mode enable or operation enabled status, bits 0, 1, 3, and 6 need to be on. So, oh well, yeah. These are all the bits that need to be on for the servo amp to be in operation enabled status. So to confirm this, we'll look at those bits. Okay. So once again, I'll be using my cyclic communication status, and then I'll be adding an AND, as I need all of those bits to be on. So, apologies. And I am looking at 5 bits, so be appending the AND block to have 5 inputs. So the first one I'll be looking at is the ready to switch on bit, which is bit 0 of the status word. Next is bit 1, which is the switch on status, which is bit 1 of the status word. Next is bit 2, operation enabled, which is bit 2 of the status word. Bit 4, which is the voltage enabled status, bit 4 of the status word, and then last but not least the quick stop, which is bit 5. So when all 5 of these bits are on, this means my server is in the operation or enable operation status, in which case I would like to turn on my status servo on. Okay. Now that we can see whether our servo amplifier is in the operation enabled status or mode, we can start looking at adding operation mode functionality. So the first one that we'll be looking at is the jog operation mode. Now, before being able to actually program or add the jog operation, we need to start looking at setting the profile velocity, the profile acceleration, and the profile deceleration. So if you recall, in the point table, all 3 of these are set within the point table. But for the jog operation, the values used are actually in the link devices, which you can see here. So it's register 06 and 07. So these values are all double words, meaning they actually take up 4 registers in the GOC memory. So setting these values, we'll be setting them on startup. So we'll be looking at setting this using one of the system variable system bits. This is similar to the always on bit, although for this will be bit 1, which is only on for the first scan cycle, if you can see here. So and we'll be looking at setting values to those variables. So first up, setting the profile velocity, which is register 0, 6, and 7. So that's our profile velocity. And then let's set a value. So if I set 1,000 here, this actually equates to 10 RPMs, as we don't want our jog speed to be too high. So setting 1,000 in the profile velocity means that the actual movement of the servo axis will be at 10 RPMs. Next, the acceleration and deceleration set at 200, which is 2 seconds. And it will basically, the acceleration and deceleration will be set to the same value. So once the GOC starts up and starts running, these values will be set in these link devices, and this will determine at what speed the jog operation will take place. So yeah. Now with these values set, we can start looking at the actual jog operation, how to command the servo to move in the jog mode. So the first step or thing to do is to actually tell the servo amplifier that you want to operate it in this jog mode, which I will quickly be looking back to the presentation. The servo amplifier uses a link device called the operation mode, which is actually register RWW00, which you input a value that tells the servo amplifier what mode you want to operate it in. So in the case for jog mode, you set this value to -100. So that would be the first step. So when I select jog mode via the HMI button that I'm going to set up or have set up, I would like to move the value -100, as this equates to the jog operation mode, which, apologies for the back and forth, but if I quickly go to my manuals, modes of operation, you can see all the values for the different modes of operation. So for the jog mode, it's -100. For the point table method or mode, it's -101. And for the other function that we'll be using, homing, it would be 6. Okay, so -100, and that is moved into RWW00 mode of operation. Now, I will be adding some interlocks here to stop more than one operation mode being chosen at a time. And this will be point table method. I do not want it to operate when jog is selected, or jog to operate when one of the others are selected. Let's insert another, and then also this one. Okay. So now I have set the operation mode as jog. However, the movement commands still need to be added. So if you recall, looking at operation mode specific, bit 4 of the control word initiates the jog movement. So this means that bit 4 of the control word needs to turn on for the motor axis to start moving or rotating. So start operation, and then let's say this is my actually I'll be using these always on so that I can have multiple options, because once again bit 4 is not just used by the jog operation mode, it's used by the homing as well as the point table method. So bit 4 needs to be turned on to execute each of those movements or motions for those methods. Okay, so next I'll have a forward and reverse, which we actually will be setting in a moment as well, but also want to interlock this that both cannot be operated at the same time. So for my HMI buttons that I'll be using, I'll set it up like this, with CODESYS being slightly finicky on this. Yeah. Actually, that's gonna cause troubles. Sorry, guys. Okay. So this will start my bit 4 of my control word, which is operation mode specific. So this means that whenever I select jog forward or reverse, I think I need to switch this. Yeah, whenever I select jog forward or reverse, the operation will be started. So the start moving command will be given to the server. Now, but operation mode specific bit 5 is used to select whether the jog needs to be in the forward or reverse rotation. So to do this, let's set this. Okay. Now, in the case of bit 5 of the operation of the control word being on for jog mode, it will mean that the axis will turn in the reverse direction. If this bit is off, it will mean the axis is rotating in the forward direction. So this means I need this bit to turn on when my forward or reverse direction is being pressed. And this will be bit 5. So that is my jogging operation in the forward and reverse direction. Yeah. Now, next step is to be able to set a home position, as we will not be able to start any positioning via the positioning table without having a home position. If you try and set any positioning sequence or activate a positioning sequence without setting a home or having a home set, you will receive an error on your servo amplifier. So next is the home position. So first step is to set home position, which, if you recall, is done by first setting the operation mode to home position, which means moving value 6 into the modes of operation mode register, which is RWW00. So when I press my set home position HMI button, and then also just interlock this so that it doesn't try and set home while positioning is active, as that can also cause an error. So also require this to not go active while jogging is selected. And then we can look at moving the value of 6 into the modes of operation. So this will set the mode of operation to home, so it will set your home position. However, it will not just set the home position when doing this. You need to activate or turn on bit 4. So the home position will be set on the rising edge of bit 4 when the homing operation mode is selected or is configured. So this means that when my set is pressed, I would like to trigger bit 4 as well. Okay, so that's actually all you need to set your home position for this operation. But to actually have the servo access return to home position, that will require the point table functionality that we included or configured there. So just as a recall, we'll be looking at executing this line for the server access to return to its home position. So to do this, we'll look at first setting the operation mode to point table. Um, and then telling it to read or put the value 101 into the operation mode, as this is the operation mode value for the point table. Also just adding some interlocks, as we don't want this operation to be executed while any other operations are being executed. Okay. Now, once again, this does not by itself execute the operation, but 4 needs to be executed. But before bit 4 needs to be executed, we actually need to tell the operation what row or what point step in the point table needs to be executed. So for this, it will be 11, meaning that we want to move 11 into the variable. Let me quickly, the target point table variable, which is register RWW05 right there. So this will be using another move in which we'll be doing this and selecting this variable. Okay, incorrect. Okay, so that now points the point table to step 11 for that to be executed once bit 4 turns on. So to add the trigger to bit 4 and make sure that it is executed in time. Wrong one. The following bit will trigger bit 4. So this will then be added to trigger bit 4, which will start the sequence. So something to note, when the point table operation is executed via turning bit 4 on, you only actually, the execution of this sequence or whatever movement is set in the point table starts on the rising edge, and you don't actually need bit 4 to stay on the entire time. So we can just pulse bit 4, which is exactly what will be done. Okay, so that now adds the return home command to the control, to the PLC program. And with this being done, we can now start looking at maybe executing the sequences that have been set up in the point table. So this actually works pretty similar to what the return to home position one works. In fact, it works practically the same. The difference being that instead of just executing one step, we have configured the point table to execute multiple steps. So this would be our point table sequence operation, and it will look similar to this, where we would be selecting point table as our mode, point table, and then also just interlocking it so that it can't try and operate at another mode or another instruction while this is being executed. Okay, so we'll also be moving the value 101 into the modes of operation, as this will also be a operation table, point table operation. But the difference being the starting point or starting step. So for sequence 1, if I just quickly bring up the point table again, for sequence 1, it will be running from point or step 1 all the way till point 10. So we just need to point it at the first step, or let's say if I point it at step 5, it will run from 5 to 10. So that's where you can play around with it a bit more as compared to what it's set as in the point table. So I don't necessarily have to point it to 1. I could point it to any point in the sequence, but it will only run up until 10. Okay, so I want it to run from point 1, which it is set as there. But because I have multiple sequences, there is some things that I need to set. So first, this only needs to execute from this point when I select my first or sequence 1. And when sequence 1 is selected, I need to pulse bit 4 or activate bit 4. And to do this, we'll be looking at doing this. And then adding this here to execute sequence 1. Now the same procedure is followed for sequence 2 with this just changing the point at which the sequence starts. So if I select this one, that's my HMI button, and then choosing what point to start at. So looking at the point table again, the starting point for sequence 2 is step 12. So we'll be moving from there on up until step 20. So setting the start point here as 12, meaning the sequence will begin at step 12. Okay, now same is done as we did here for sequence 1. And we also need to pulse the bit. Okay. So that is actually all the movement operations that we'll be adding to the servo functionality. Next up, we'll be looking at how to actually reset the amplifier when an error or an alarm has occurred. So to do this, the bit in the control word, bit 7, needs to be turned on. When bit 7 is turned on, it sends the reset command to the servo amplifier, which resets the servo amp. Now note, if the cause for the alarm is still active, resetting the servo amplifier will do nothing, as the alarm will just reoccur. So make sure to only reset the servo amp once the cause for the alarm has been resolved. So this is pretty simple. It's selecting a HMI button to turn on the command bit for the reset. Which is RW01 bit 7 as such. Okay, so that is the PLC programming that we'll be requiring for this demonstration. Now, I have gone and set up an HMI screen beforehand, as there's a lot of ground to cover for this demonstration. And this just helps to keep us within the time frame. But I'll quickly give an overview of what has been set. So simply, this is the Servo On HMI button. So that's where you activate the Servo On command. And this is the lamp, which turns on green when the status reflects that the servo amp is on. Okay, I'll be coming back to the alarm in a bit, because that is purely on the visualization side that this was set up. Now, next is the jog selection, forward and reverse rotation. So how this works, how it has been set up. The jog button is a toggle button that selects the jog operation mode, and the forward and reverse buttons, if you recall from the PLC program, activates the forward or reverse rotation. So these are momentary buttons, meaning the contacts will only stay on for as long as you are pressing these buttons. Similarly, the set home and return home buttons, they are also momentary, or tap as they are referred to within CODESYS. So they only stay on for as long as you tap it, but this, when pressed, sets the home and returns the server axis, or causes the server axis to move to its home position when the return home button is selected. Next, the point table button is similar to the jog. When this is pressed, the jog point table mode is selected, and this is also a button that is toggled. So when that is selected, you are able to press sequence 1 or sequence 2 for either the sequence 1 or 2 to be executed. This is also momentary buttons, so it's only the contact's only active as long as you are pressing it. Now, for the reset alarm, that HMI button in the program turns on when this button is pressed, and it's also a momentary button. Now, to point out the three things that didn't require any PLC programming and is purely represented in the HMI side of things, is the alarm, the operation mode display, and the position. So for the alarm, there is a read link register. So I think it's register RWR 12 and 13 that stores the current alarm value. Now, this is a double word, and it does store the value in hex. So keep that in mind. Now, I think one of the best ways for me to show you this is via my presentation. Okay, so the to display the alarm in the way that the servo amplifier would display it, which if you see the AL 50.4, that is how it is displayed on the servo amplifier itself. But to do this for the HMI side of things, it needs to be split into two different displays, meaning that the register needs to be split in two. So to do this, the most significant word and the least significant word of this register needs to be attributed to the correct side of the alarm, in which case the most significant word will be the value before the dot operator or the point, and the least significant word would be the value after the point. As such, it is configured to display on the HMI screen by using two different display objects. Now, when it comes to the operation mode, there is a register in your RWR register 00 that displays the mode of operation. So it gives feedback from the servo amplifier to the GOC to indicate what mode the servo is actually in. And this is displayed via dynamic text on the HMI screen. And to do this, a text list is created. So if I go to my device tree on the left-hand side, you'll see there's an operation mode text list. So basically what is here, the ID of the entries are set to the values that will reflect what operation mode the servo motor is in, which is -101 for the point table, -100 for the jog mode, and 6 for homing method. And when the value of the variable set is reflected by one of these IDs, the corresponding text in the default column is displayed. So if I go to my dynamic texts configuration, you'll be able to see that I've set the modes of operation register there. So that means the value reflecting the operation mode will determine what is displayed in this visualization object. Last but not least is the position of the servo motor being monitored. This is monitored via the position actual value register, which is RWR08 and 09, so also a D word. And once again, this will be in terms of pulses. It's quite simple. This variable is just configured to display in this visualization object. If you do want to see the exact configuration of each of these visualization objects, they are detailed in the presentation. So yeah, you'll be able to recreate the screen via the presentation, which I will be sharing once we are finished. Okay, so that leaves us with actually building and downloading the program to the GOC to test whether this is actually working. So my build and rebuild, let's check. Doesn't seem to be bringing up any errors. So I'll now be looking to download my program to the GOC. Okay, so the program has asked me to download, which I will do. Once it's downloaded, the GOC first needs to be set to run mode via the play button you see right here. And then I will be pressing buttons on the HMI screen, but I will be showing you the actions within the PLC program code. Okay, seems like the download is finishing up. Now you can see it is currently stopped. So pressing play will now start the program running. Now, first up, because I disconnected the communication between my server amp and my controller, the server amp will actually go into error because it's no longer able to communicate with my controller, which if I quickly check, you'll see the alarm there. Although the alarm that is displayed on my screen is in hex, as this is generally how the alarms for the server amplifiers are coded, it displays 086.1. So that would be the alarm that you go look up in your manual. So first up, the alarm needs to be reset. So looking at the ladder code for this, if I press my reset button, you'll see it turn on. And when I now try and look for the alarm code, you'll see that it is now 0. There, it's 0. And if I also look at my status bit for my fault, which is bit 3, it is also false. So if I look at my current position, which is position actual value, you see that it's currently on 75 pulses. So this means it is 75 pulses in the positive direction away from home position. But let's say I set my home position where it currently is when pressing the button. Let's just make so that you can see the ladder code as well. So homing, yes, set home position. So when I press, you'll see the mode of operation value going to 6, and you'll also see this position actual value go to 0. Sorry, apologies. I forgot one crucial step. The server needs to be turned on, otherwise I can't actually command it. So you're able to reset the server amplifier without the server on command, but you can't command it to do any movements. So first up, let's actually do the server on. So you can see the server on going, turning on, and the status coming back that the server has actually turned on. So now that that is done, we can actually set home position, which you can see the actual value change to 0 now. And you can also see the mode of operation has changed to 6. So first up, let's try a jog operation. So if I select my jog mode, so select the jog button on my HMI screen, you can now see the operation mode change to -100, which is the jog operation mode. So if I now click my forward button, you can see the position of the actual position value change. So if I just quickly scroll down to bit 4, where you can see it being activated, you'll see the bit turning on as I press. If I do the reverse rotation, it looks similar for bit 4, but if I go back up, let's say go back up to my jog operation, you'll see bit 5 turn on because I am now instructing it to turn on in or rotate in the negative direction. Okay, now deselecting jog mode, I now want to have my server access go back to home so that I can actually start my sequences. So to do this, I just press the return home button on my HMI screen, and you'll see, well, this changed to -101, this changed to 11, and you'll see the position actual value changed until it ultimately reaches 0. You'll see it's still adjusting, but yeah, it is now returned to 0, so home position. Okay, with home position set, let's try and do a sequence. So to do this, I select point table as my operation mode via the HMI button. Okay, that's gonna be, that's a mistake actually. Okay, so apologies, this interlock is not supposed to be there. It's actually stopping the thing, so let's quickly redo this. I can go show the sequences of the point table. So the download is completed once again. So once again, fault should be on because the communication was broken. Yeah, so see the fault bit turn on. When I reset it, it will turn off, and then also turn on the server on command. And because it turned off, I'll just have to return it to home as well, which it now is. Let's see where the current position is. Okay, position actual value. So when I now once again select my point table method, you can actually see it changing to -101, but now I have not selected which sequence I want to execute yet. So depending on what sequence button I execute, it will select that starting point. So starting off with sequence 1, you'll see position moving, and it will ultimately go back to 0, as that is what is set up in the point table. And that completes sequence 1. So if I now select sequence 2, it will now start that mode or that sequence, and you'll also see this change to 12. Okay, change to 12, and it's currently moving according to sequence 2. Okay, and that is sequence 2 complete. So that is actually all for today's demonstration and webinar. So are there any questions regarding today's topic?
How many
Yes.
in a table of movements? How many positions can you have? Is there a limit?
Yes. I think it's
256.
255. Well, yeah,
Okay,
255. Yeah.
so you have to be quite stingy with these things.
Yes, relatively. Any other questions? Okay. So the next webinar on the GSC in the GSC series will be regarding the Modbus TCP slave configuration of the GSC itself, And in this case, we'll also be configuring an FX5 as the Modbus TCP master and showing how the communication works between the two. This will take place on the 19th of November of 2025 this year, so in 2 weeks' time, in the normal time frame of 10 to 11:30.